Chapter 4, Section 4, the Fundamental Theorem of Calculus. You can kind of tell by the title of this section that this is an important one. There are two branches of calculus, so I've talked about it several times in the other videos, and differential calculus and integral calculus. Those are the two branches, and they seem somewhat unrelated, although by now I'm hoping that you could kind of get the idea that one kind of undoes the other. Well, it's the fundamental theorem of calculus that kind of connects these two. Now, the fundamental theorem of calculus was developed over a long period of time, and it wasn't really put together until like the 1950s. But it was mathematicians Leibniz, Newton, Cauchy, which I know I mispronounced, Poisson. There's a name you haven't heard before. Now you'll hear his name quite a bit in statistics. Poisson described how the definite integral, which we defined in the previous video in section 4.3, to be the difference of the antiderivatives f of b minus f of a at the endpoints of a closed interval from a to b. Now, all these important ideas, Leibniz and Newton working on their main concepts, Cauchy kind of, I don't want to say tweaking the information, but putting it together using the limit definition, and then Poisson, who I believe was in the 1600s, if I'm not mistaken, 1700s. All this was kind of tied together, as I mentioned, by mathematicians in the 50s, and these concepts that were brought together were called the fundamental theorem of calculus. Now, the fundamental theorem of calculus is kind of a longer theorem, and there are two key parts. So what they do a lot of times, and this book does this as well, is that they break this into two parts. The first part on how to evaluate a definite integral, and then the second part, how it shows how differentiation and integration are kind of like inverse operations of one another in the second part of this. So anyway, the first part of the fundamental theorem of calculus says that if a function f is continuous on a closed interval from a to b, that's lowercase letter f, and if capital F is the antiderivative of lowercase letter f on this interval, then the definite integral, which up to this point we either have to use a limit process or at best maybe area under a curve to evaluate, it says that the integral from a to b of f of x dx is capital F of b minus capital F of a, which means you take the antiderivative, you substitute in the upper limit of integration, and then from that you subtract what you would evaluate when you plug in the lower limit of integration. The proof is not overly involved. It's got some stuff to it. It's in the book. I used to kind of run through the proof with my students, but it seemed like I was just doing more, adding more confusion in some ways than helping out. But I will mention that the proof involves the mean value theorem, which we studied in an earlier chapter. Now we're going to get to another mean value theorem. The first one that we've studied was having to do with differentiation. The mean value theorem that we're going to study in this section has to do with integration. So the same name, but two different theorems. So the guidelines for using the fundamental theorem of calculus, I like to abbreviate this because I'm too lazy to write it out every single time, is that if the antiderivative of f can be determined, we can evaluate it without having to use the limit of a sum. And that the fundamental theorem of calculus, we use the notation, looks like this. The integral from a to b of lowercase letter f of x dx is equal to capital F of x. Notice the bar right here. Kind of means that we're evaluating it at, there's our lower limit, there's our upper limit. So we substitute the upper limit in first and subtract from that what we get when we substitute in the lower limit of integration. Okay, make sure that it's upper minus lower. If that helps you to keep track of that. Now notice here, I don't have a plus c because the constant of integration cancels out. If you look at this with a constant of integration, so we take the antiderivative of lowercase letter f of x dx, we get capital F of x plus a constant. Then we evaluate it first by plugging b in, then by plugging a in. And we get rid of the parentheses here. The c's are going to cancel out, and that's kind of hard to see there, but you just get f of b, capital F of b minus capital F of a. So we only put down the plus c for indefinite integrals. Here's an example. Evaluate this definite integral. First I integrate, and I can integrate this conveniently. The power rule, 1/2 x squared minus 5x. And I'm going to evaluate this, and I use this little symbol here, from 1 to 3. So first we plug the 3 in. Now, I can imagine that if you plug 3 in, you guys can do the arithmetic in your head, but for at least the first one, I'm going to write it out. So this is going to be 1/2 times 3 squared minus 5 times 3, and then I subtract from that. Note the parentheses so I don't mess up on my signs, because I'm subtracting all of this. There's usually more than one term here, so be careful. Plug 1 in, I get 1/2 times 1 squared minus 5 times 1. So let's see, this would be half of 9, 9 halves minus 15, which would be 30 halves. So 9 halves minus 30 halves is negative 21 halves. Careful with your arithmetic. Minus, this is going to be 1/2 minus 5. So that's negative 4.5 or negative 9 halves. So I have negative 21 halves minus negative 9 halves, like adding the opposite. I'm going to get negative 12 halves, which is negative 6. Remember that a definite integral is going to give you a number. It's equal to a number, even if I do turn my page sideways again and again and again. Sorry about that. All right. Next example. All right, and we have the definite integral from 1 to 9 of f, or 5 times the square root of x dx, which I'm going to write the integral from 1 to 9 of 5 times x to the 1/2 dx. So I'm going to use the power rule here. I'm going to go up, add 1 here, so that'd be a 3/2, and then I'm going to divide by 3/2, which is the same as multiplying by the reciprocal of 3/2, which is 2/3. And I have a 5 there, so 5 times 2/3 is 10/3 x to the 3/2, running from 1 to 9. Now, if you'd like, you can go ahead and put that constant out in front and then multiply it times what you get when you evaluate it at these limits. So first I'll plug in 9, so that's 9 to the 3/2 minus 1 to the 3/2. 9 to the 3/2, you take the square root of 9 and cube it, that's 27 minus 1, that's 26. So this is 10/3 times 26, which is like 26 over 1, or 260/3. There's my answer. Up here, one involving trigonometry, if I integrate cosecant squared x dx, which is one of our formulas that we have, this is negative cotangent x, and we're evaluating this from pi over 4 to pi over 2. So this is negative cotangent of pi over 2 minus negative cotangent of pi over 4. Again, careful with your signs. Lots of silly mistakes can be made here. So the cotangent of pi over 2, that's the cosine of pi over 2 over the sine of pi over 2, which is 0. So this is just the opposite of 0, which is 0, minus. Now this is going to be negative cotangent of pi over 4. Well, the cotangent of pi over 4 is the cosine of pi over 4 over the sine of pi over 4, which is square root 2 over 2 over square root 2 over 2, which is 1. So this is a negative 1. So I have 0 minus a negative 1, which is positive 1. Now this next guy is a little different because of the absolute value bars. I just can't integrate this with absolute value bars. I don't have a formula for that. So I have to somehow get rid of the absolute value bars. Now think about what's going on here inside the absolute value bars, x minus 1. X minus 1, the key value here is 1. Because if I put 1 in, I get 0. If I put in anything bigger than 1, then this is positive. If I put anything smaller than 1, then this is negative. And with the absolute value, it's got to be positive. So I'm going to break this apart into two integrals, from 0 to 1, that's where it would be negative, and from 1 to 2. And this is the additive integral theorem that we had before. And this is going to say that now, from 0 to 1, this is where it would be negative. X minus 1 would be negative, so I have to have absolute value. I have to have it positive, so I need the opposite of x minus 1. I need 1 minus x. But from 1 to 2, these values would make it positive, so I don't need the absolute value bars. I just need x minus 1. So now I can go ahead and I can integrate this. This is going to be x minus 1/2 x squared, running from 0 to 1, and then I'm going to add to that 1/2 x squared minus x, and I'm running from 1 to 2. So if I plug 1 in, I get 1 minus 1/2 is 1/2, minus, if I plug 0 in, I just get 0. I'm doing the arithmetic in my head. I'm hoping I'm not messing you up here. If you need to put the steps down, write the steps down until you feel more comfortable with it. Plus, plug 2 in. I get 1/2 of 2 squared, which is, so 1/2 of 4, which is 2, minus 2, that's 0, minus, and then I plug 1 in, I get, what do I get here? I get 1/2 minus 1, that's negative 1/2. So I get minus negative 1/2, that's plus 1/2, and I get 1. There's my answer. Now this next example is talking about finding the area of the region bounded. The area of the region bounded, as we talked about in the last section, is defined as a definite integral. Let's see if I can come up with a halfway decent looking sketch here. I like to sketch these out when I am finding the area under the curve so that I can see exactly the region that I'm working with. So I'm going from x equals -1 to x equals 2, and it's got to be above the x-axis. Well, at -1, I'm at 2. At 0, I'm at 1. At 1, I'm at 2. And at 2, I'm at 5. 2, 3, 4, 5 right there. So it's going to look like this, kind of. At 2, at -1, and of course this is the x-axis. Well, since we have defined the area under this curve as the definite integral, I'm going to write the definite integral going from -1 to 2 from my lowest value of x to my largest value of x that's on this curve. And this is of the curve x squared plus 1 dx. So this is going to be 1/3 x cubed plus x, running from -1 to +2. Now you're going to encounter fractions in many cases when you're evaluating a definite integral, because when we integrate, and especially when we're using the power rule, we add 1 to the exponent, but then we divide by that new exponent, that number, and that's going to lead to a lot of fractions. So don't jump on the grab my calculator and punch it in and use a decimal. Go ahead and take it out as fractions, unless it's just completely unreasonable, and this is not the case here. I plug 2 in, I get 8/3 plus 2 minus, then I plug -1 in, I get -1/3 minus 1. So this is 8/3, this would be 6/3, so I get 14/3 minus, this is going to be a -4/3. So subtracting a negative, same as adding the opposite, I get 18/3, which is 6. And this would be square units because it's actually finding an area. So that wasn't unreasonable. See how simple it turned out to be. You know, I get something like 5.999 or something like that. I'm wondering, why can't you just do a little bit of arithmetic with fractions? Now, with this is kind of what I was discussing here, how this definite integral is defined as the area under the curve. But with this, I want to introduce a new idea, which is called the mean value theorem for integrals. Now, the mean value theorem for integrals says if f is continuous, of course, we know mean is kind of like average. If f is continuous on a closed interval from a to b, then there exists a number c. So it sounds like an existence theorem. It doesn't tell us how to find the number c. It just tells us there exists a number c that's in the closed interval from a to b. It could be at an endpoint, such that the integral from a to b of f of x dx is f of c, whatever the c value is, times b minus a being kind of like the length here of my region. So I am going to take this, and from this evaluate or come up with another key idea, a definition. But what this is saying here is that the area under the curve is equal to some value c, and I don't know where c might be. Maybe c is right here, such that f of c, that would be this distance here, f of c, be the y value here, it'd be this distance, times b minus a is equal to the area under the curve. Well, let's think about that. If I was to draw a horizontal here, I'm going to try to draw a halfway decent horizontal. I'll use a green pencil so you can see it a little bit better. F of c, that's this distance here, times b minus a, that's this distance here. Wouldn't that be the area of this rectangle? So they're saying that there's some rectangle in here on this continuous function that's going to have the same area as the area under the curve. It's kind of neat. Now, as I mentioned, this theorem leads us to a definition which is always on the AP test, and that's the average value of a function. The average value of a function goes hand in hand with the last theorem, as you'll see here in just a second, it says let f, if f is integrable on the closed interval from a to b, then the average value of f on the interval is 1 over b minus a, the integral from a to b of f of x dx. Now, the average value of f, so that's the y's. So let's go back to my diagram here, which I threw to the side. If I have y equals f of x here, and if I was somehow able to add up all the y values on every point, which of course is impossible because there's an infinite number of points on this interval, but if I was able to add up all the y values and just like an average, divide by how many there are, I would get the average value of every y value that's on here from a to b. This is saying I can find that here, because of course it's impossible to do it with arithmetic, but I can use a definite integral and find that average value. I can find that average y value. Now you say, well, how is it related to the mean value theorem? Well, look right here. If I was to divide both sides by b minus a, and of course b minus a dividing into this is the same as 1 over b minus a times it, you can see I have this expression. So this f of c, this value of c that exists, this f of c, this is my average value. I just don't know how to find c. I know it's there, but probably going to have to take some algebra to figure it out. The area of the region under the graph of f is equal to the area of the rectangle whose base is b minus a and whose height is that average value, which in the previous theorem I called f of c. So let's find the average value. We may not be able to find c, but we can at least find the average value if we use this definition right here. Put this to memory. That's a good one. So this is 1 over b minus a, this is my a and my b, so it would be 3 minus 0 from 0 to 3 of f of x, which is the expression 2x squared plus 4 dx. So this is 1/3. I'm going to integrate, so this is up to 3 over 3, so 2/3 x to the third power plus 4x running from 0 to 3. So this is 1/3. If I plug 3 in, I get 3 to the third power, which is 27. 2/3 of 27 is 18, plus 4 times 3 is 12, that's 30. Minus, plug 0 in, well that's easy, that's just a 0 in this case. So 1/3 of 30 turns out to be 10, and that's my average value. Now, can I find the value c that makes this equal to 10? Well, I'd have to think of this as 2c squared plus 4 equals 10. 2c squared equals 6. C squared equals 3. C would be plus or minus the square root of 3. Of course, we'd have to just stick with the positive because my interval is from 0 to 3 here. So it would just be a positive square root of 3. Sometimes it's easy enough that we could figure out that value of c, but my average value is the 10 for this function on that closed interval. So that's kind of cool, and that's useful. And now what I want to do is I want to get to the second part of the fundamental theorem of calculus, and to do that, I'm going to first talk about what we have so far with the fundamental theorem with a definite integral. The definite integral is equal to a number. Our constants, a and b here, our function f of x is a function of x dx with respect to x that we integrate. Now, let's change one of these constants to an x, where f is a function of x right here. Okay? So what's going to happen is I'm going to put an x here as a limit of integration. It's usually the upper one that you'll see this. I'm going to call this function a function of x here from a to x of f of t dt. Now you say, well, what happened to the x's here? Well, I've got an x here, so I want to make sure that I can tell the difference here. So I change my independent variable and I put it in terms of t, which is the other independent variable 99% of the time. So this is no longer going to give me a number. It's not going to give me a number like the definite integral did here. It's going to give me a function of x. Now you say, well, how do you get that function of x? Well, I'm going to show you that in just a second, but I want to make sure that you understand that f of x is what we call an accumulation function. It's accumulating the area under the curve from y equal f of x, t equal a to t equal x. So what happens here is, here's some curve, y equals f of t. and this is from A perhaps to B here. And so we're looking from A to X, where perhaps t equals x might be somewhere around here. It's accumulating the area. As x gets bigger, it's adding more area to it. So it's an accumulation function. Now you say, well, I'm not sure I'm really getting this right now. Well, we're going to spend more time about this, but the idea here is that you are able to find this using the second fundamental theorem of calculus. Theorem. The second fundamental theorem of calculus says that if f is continuous on a closed interval I containing a, then for every x in the interval, if I take the derivative of the definite integral from a to x, so this is a function, this is the accumulating function I was just talking about, that I will get my function of x, f of x, that I will get that value. So you say, well, wait a minute, all this looks like you took a derivative of a definite integral that had an upper limit of x. It just looks like you plugged the x right in there and wrote your answer. And that's kind of how it turns out, as long as this is an x. Now, when I was first looking at this when I was in calculus, I thought this is easy. I'm just going to have to remember to put the x in. And that's the case in most of the problems. But some of the problems don't have just a single x here. They'll have a function of x. And so there's a little bit extra. So I'm going to show you that here in just a moment. But first, let's try using the second fundamental theorem of calculus to evaluate this derivative of this definite integral. Now, notice up here it says that the second fundamental theorem, this is one of the things it says, that f is continuous, then it has an antiderivative. We kind of talked about that before as well. So I'm going to evaluate the derivative of the integral from 0 to x of t squared dt. And I'm going to do it two ways. First, I'm going to do it the old-fashioned way, and then I'm going to show you how it matches up with the second fundamental theorem of calculus. So first thing first, the old-fashioned way. So first I'll do this part inside here. This is going to be the derivative with respect to x of 1/3 t to the third power running from 0 to x. So this is the derivative of 1/3 x cubed minus 0, which of course is just 1/3 x cubed. So the derivative of 1/3 x cubed is equal to, not 2. The 3 cancels with the 3. The 2 is the exponent. I'm going to get x squared. Now, that's the first way. According to the second fundamental theorem of calculus, the derivative with respect to x of the integral from 0 to x of t squared dt, as I mentioned before, this is where I thought Dr. Ringenberg just wanted me to plug the x right in, but look what happens if I just plug the x right into this expression. I get x squared. Now, this is okay, but sometimes you get a function here that you just can't integrate. So this kind of bails us out. So on functions that it's more difficult to integrate, we're able to find those derivatives using the second fundamental theorem of calculus. Here's an example of one. I mean, I don't know off the top of my head how to integrate this. I could probably figure it out, but it's going to use some calculus 2, not so much calc 1, which is what we're studying now. So I'm going to use the second fundamental theorem of calculus. Good old Dr. Ringenberg, just plug that x right in there, and I would get the square root of x to the third plus 1. I don't have to go through all these steps. Now here's where it gets a little different, because in this particular problem it says find the derivative of capital F of x from the integral from pi over 2, it could be any constant, doesn't always have to be a 0, it can be any constant here, to not x but x cubed of the cosine of t dt. So if I'm trying to find the derivative, I'm trying to find capital F prime of x, which is the derivative with respect to x of this integral from pi over 2 to x to the third of the cotangent of t dt. Well, you kind of still start out this problem by doing the same thing that I was kind of showing you the shortcut before. This is a constant. I'm going to substitute this expression right in for t. And I would get the cotangent of x to the third. Now, I'm not done. That's what I thought would work before, but then I realized I'm taking the derivative and I have a composite function. So I've got the derivative of this, but I have to do the chain rule and take the derivative of the inside function. So this is going to be times the derivative of x cubed, which is 3x squared, or better yet, I'm going to write 3x squared, the cotangent of x to the third. There's a lot of information in this section, which I ran through kind of quickly. If you need to watch the video again or run through this information in the book or watch somebody else's instructional videos on this, then I don't blame you, because it's important information. You do need to do a lot of practice, because the definite integral is what we use for applications of integration, which is coming up in Chapter 5. So we have a little bit more with integration to finish off this chapter, but you really want to feel comfortable with taking a definite integral as we were doing back here. So practice, practice, practice.